Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is industrial wind turbines. Our objective is to identify the basic parts of a modern industrial horizontal axis wind turbine generator and examine the operation of a wind turbine on an introductory level. This lecture presumes the viewer has watched the Introduction to Renewable Energy and Wind and Water Power lectures, both available at the Big Bad Tech channel. Additionally, this lecture presumes the viewer has a background in DC, single-phase AC, and three-phase AC electrical circuit analysis, hydraulics, motor control, motors and generators, has attended a hands-on industrial mechanics course with a working understanding of hand and power tools, fasteners, torque and tensioning, gears, gearboxes, bearings, lubrication, and shaft alignment. Presuming you're among the worthy, let us begin. They're not windmills because they don't grind grain. They're not cow coolers because they're not fans. They don't pump water, nor do they give whales cancer. They're wind turbines, and they produce electrical power. Wind is becoming an increasingly economical means of producing electrical power from renewable resources, and the demand for wind turbine technicians with a strong background in electromechanical technology is high and expected to increase. A very basic description of a modern wind turbine generator includes a rotor, which consists of a hub and 3 blades. The rotor is the principal means of initially capturing the incoming mechanical power of the wind prime mover and turning it into rotating mechanical power input to the main shaft. A step-up gearbox takes the high torque, low speed output of the main shaft and converts it to comparatively lower torque, higher speed output of the high speed shaft as input to a generator which outputs usable electrical power. The nacelle houses the gearbox, generator, and other accessory elements mounted at the top of a tall tower that exposes the rotor to high wind speeds. 2 fundamental movements define wind turbine mechanical control: pitch and yaw. To pitch is to change the angle of the blades relative to the hub. Inside the hub, hydraulic or electrical pitch systems feather or change the angle of the attack of the blades, such that they capture or shed more or less incoming wind power, thereby influencing mechanical power input, thus electrical power output. To yaw is to rotate the nacelle relative to the tower. Between the nacelle and tower, yaw motors horizontally rotate a turbine into or out of the wind and expose more or less of the rotor area to the incoming wind. We'll significantly expand upon this basic description of a wind turbine in this particular lecture. Today we'll take a closer look at the elements comprising the rotor, including the blades, hub, 2 types of pitching mechanisms, electrical and hydraulic, those elements inside the nacelle including the drivetrain consisting of the main shaft, gearbox, high-speed shaft, coupling and parking brake, the generator, controller, as well as the tower and other accessory elements, including power distribution, power conditioning, and performance monitoring systems. Later lectures will take a closer look at some of these subsystems in greater detail. Modern industrial wind turbines are known as horizontal axis wind turbine generators, abbreviated as HAWT, where the generator is located at the top of the tower and the axis of rotation turns horizontally. This is in contrast to a vertical axis wind turbine generator, or VAWT, where the generator is located at the bottom and the axis of rotation turns vertically. A vertical axis wind turbine can harness wind energy from the wind regardless of the direction the wind blows. As an illustration of this process, imagine taking a 55-gallon barrel, cutting it vertically in half, then gluing the 2 halves offset from one another, then installing this assembly onto the vertical shaft of a ground-mounted generator. When wind from any given direction strikes the generator, the concave side of the barrel captures the wind and the convex sheds it, such that the wind turns the generator shaft, and with sufficient speed and torque input, the generator produces electrical power output. This is true if the wind blows from the north, the south, the east, or the west, implying that a vertical axis wind turbine generator does not need to actively yaw or to turn itself into the wind and naturally passively orients itself to the wind regardless of wind direction. Another advantage of the vertical axis wind turbine generator is that the generator is not installed at the top of a tower and is instead mounted at ground level where it's easy to service and repair. As advantageous as these 2 features may be, the principal flaw in the design of a vertical axis wind turbine generator is that it is not windy at ground level, and better wind speeds are achieved well above the surface. At the surface there exists wind shear, which is a change in wind speed and direction over a short distance, and turbulence, which is chaotic, unstable flow. As a general rule, an object of height h disturbs a hemispherical region 20h in diameter and 2h in height. You note this includes a region 2h in front of the object as air piles up in front of the obstruction and slows down. As we learned in the wind and water power lecture, available at the Big Bad Tech channel, the power present in a column of moving air is dependent upon several properties, specifically the density of the air, the area of the rotor, and the wind speed, specifically the cube of the wind speed, meaning any increase in wind speed has a significant effect on wind power input, thus mechanical power output. Getting outside and above this disturbed region is perhaps the horizontal axis wind turbine generator's single most important advantage. Given wind speed's substantial contribution to wind power input, it makes sense to maximize this contribution and expose the rotor to not only increased wind speeds, but also more favorable, less turbulent wind conditions than below. This necessitates the rotor, gearbox, and generator be placed at the top of a tall tower, which does significantly complicate repair, service, and control. However, means a horizontal axis wind turbine can produce significantly more power than their dumber, less functional vertically oriented relatives confined to the surface. This lecture exclusively deals with horizontal axis wind turbine generators, and for the remainder of this discussion, I will drop the qualifier horizontal axis from now on and simply refer to them as wind turbines. There are two principal wind turbine designs that refer to the orientation of the rotor: downwind or passively yawed wind turbines, and upwind or actively yawed wind turbines. A downwind design, as the name implies, lets the wind passively push the rotor mechanism of the wind turbine downwind of the tower as wind would unfurl a flag from a pole. While this passive orientation mechanism is admittedly inexpensive, it's not super ideal, since anytime a turning blade enters the obstructed space behind the tower, it encounters turbulence in the wind shadow of the tower, and sometimes it emits an undesirable popping noise. In fact, a lot of the complaints about wind turbine noise reference these old-school wind turbines. In addition to excess noise, a downwind turbine does not make use of the full surface area of the rotor, since a portion of it exists inside the wind shadow of the tower, thus leading to inefficient operation. For this reason, no one builds downwind turbines anymore, and modern manufacturers have adopted an upwind approach. An upwind design, as the name implies, necessitates the rotor be actively positioned upwind of the tower, continually facing into the wind. This requires some hardware and control upgrades, however it's worth the expense given the increased output and reduction in noise. Old-school wind pumps and small residential-scale wind turbines often use a small tail to passively orient their tiny rotors upwind. However, modern giant wind turbines are way too massive for this passive means of orientation management and must resort to active control. The act of horizontally turning a wind turbine into or out of the wind is known as yawing. Thus, upwind turbines are known as actively yawed wind turbines. As we learned in the wind and water power lecture, the efficient capture of wind power necessitates an upwind turbine exposes as much of the rotor surface areas as possible to incoming wind. This necessitates a wind turbine know where the wind is coming from, where it is pointed at, and a means of effectively closing the distance between the two. Components of a basic yaw system include switches and sensors that act as inputs, actuators like electrical motors and brakes that produce some output, and a control system which manages outputs based on input conditions. The nacelle itself sits on top of the tower on an externally or internally toothed slewing bearing, allowing the nacelle and tower to mechanically rotate relative to one another. Yaw motors affixed to the nacelle bed plate or platform mesh with the slewing bearing via a gearbox intermediary. More on gearboxes later in this lecture. To park the nacelle in place, the yaw system may utilize spring-applied, electrically released friction brakes right on the motors, or, if the nacelle is sufficiently massive, independent hydraulic brakes which grip a brake disc on the slewing bearing. If the yaw controller indicates it's necessary to yaw from one position to another, the yaw brakes are disengaged and the yaw motors energized in one direction such that the nacelle and rotor attached to it move relative to the tower and face the incoming wind. Once the nacelle and rotor arrive at the designated position, the yaw motors are de-energized and the brakes applied. In summary, brakes off, motor on, then motor off, brakes on. As a means of determining present yaw position, a yaw system often utilizes an incremental rotary encoder. One method of implementing an incremental rotary encoder is known as an AB encoder that uses shaft-mounted gear to mesh with the yaw ring teeth. When the nacelle turns relative to the tower, the encoder rotates a specific number of turns per degree of revolution. The shaft of the AB encoder uses two sensors, slightly offset from one another such that when the sensors receive A, then B, it means the shaft is going clockwise. If, however, the sensors receive B, then A, it means the shaft is going counterclockwise. Beyond rotational direction, AB encoders also include a third signal, Z. You'd think it'd be C, but it isn't. It's Z. The Z, or index signal, happens once per revolution and serves as a way of determining an absolute position for the last full rotation. The number of AB pulses since the last index signal can be used along with the gear ratio to determine yaw position with a desired degree of accuracy. Alternate methods of determining yaw position include non-contact magnetic proximity detectors, which count the passage of teeth in the yaw ring. Inside a wind turbine tower, a large bundle of cables transfers power from the generator in the nacelle to the power conditioning equipment and transformer at the base. As wind direction shifts throughout the day, there may be occasions where a wind turbine follows it in a complete circle, north to east to south to west, and then another full circle from north to east to south to west in the same direction. For every full turn in one direction, the output cables of the generator get twisted together, and given a sufficient number of turns in the same direction, it may tighten the cable bundle to a degree they suffer damage. For this reason, in addition to keeping track of present angular position, the controller also keeps track of how many full revolutions in one direction have been accomplished. At a certain point, maybe 3 or 4 full twists in one direction, the controller is like, enough. Let's unwind, and momentarily halts production to unwind an equal number of full turns backward in the opposite direction, resetting the cable bundle to a slack position. Additionally, the turbine controller takes advantage of extended periods of low or no wind conditions when production ceases to take the time to unwind to a slack condition. The obvious problem with this arrangement is this. What if the controller forgets how many full turns it made in one direction? I mean, it happens, right? Industrial systems sometimes experience unexpected shutoffs or errors that wipe out data. For this reason, turbines also include a backup electromechanical twist switch that is essentially a limit switch tied to the cable bundle. If the turbine ever forgets the number of turns it's made and the cables keep getting twisted up, eventually they pull so hard on the twist switch, it's triggered and it's like, hey dummy, you lost? And the controller is like, oh yeah, I should probably unwind. In this sense, the hardwired electromechanical twist switch acts like a backup to the incremental rotary encoder and software-based positional data in case the controller ever loses its mind, which is always a possibility. Brief aside, viewers may wonder what happens if the controller forgets the number of turns and the twist switch is broken. Well, I'll tell you what happens. The turbine keeps turning and turning and turning, and the cables keep twisting and twisting and twisting until about 17 turns in one direction, the super twisted cables fail and the whole turbine faults out. True story. Two of the most critical inputs for a wind turbine yaw control system are housed in a wind station at the top of the nacelle. These are the wind vane and anemometer. The wind station additionally includes obstruction lights. The obstruction lights aren't sensors critical to the yaw system, but since they're mounted in the same vicinity as the wind vane and anemometer, we may as well discuss their role while we're here. A wind vane is an instrument that measures the direction from which the wind is blowing. The wind catches the rudder blade of the wind vane and makes it rotate such that an encoder at the base quantizes the wind direction and sends this directional data to the control system. In summary, a wind vane lets a turbine know if it's pointed straight into the wind like you want, or if the wind is hitting from the side, the back, or some other suboptimal angle. An anemometer, in contrast, measures wind speed. As with a vertical axis wind turbine, the concave side of the cup anemometer catches wind and the convex side sheds wind such that it rotates at a rate proportional to the wind speed. The faster the wind speed, the faster it turns. A counter at the base of the anemometer counts the number of revolutions for a specific time period and quantizes this as a wind speed and sends this data to the control system. These two sensors, the wind vane and anemometer, deliver critical data to a wind turbine control system, specific wind direction and wind speed. Wind direction is essential to ensuring the nacelle is pointed in the right direction, thus maximizing the rotor swept area exposed to wind, whereas wind speed is essential to ensuring the blades are pitched at an appropriate angle to maximize energy production. In an ideal condition, with the nacelle pointed in the same direction as the wind vane indicates the wind is coming from that same direction, thus flags straight backwards. If our wind shifts such that it hits the turbine from the side, or worse yet, totally reverses direction, and a difference in the wind vane and nacelle orientation indicates it's time to yaw and close the gap. Brakes off, yaw motors on, traveling in the direction that yields the quickest route. Once the wind vane indicates the nacelle has reached the new destination, yaw motors off, brakes on. Given wind turbines are exposed to inclement weather, which might include icy conditions, note these electromechanical style wind vanes and anemometers can sometimes freeze or break, which essentially blinds a wind turbine to wind conditions. For this reason, some wind turbine manufacturers have experimented with ultrasonic wind sensors, which combine the function of both wind vane and anemometer in a single housing to simultaneously measure wind speed and direction with no moving parts, thus increasing reliability in hazardous weather conditions. These style of wind sensors bounce tiny ultrasonic signals back and forth between their probes, and believe it or not, can sense in which direction and how fast these signals drift and quantize it as wind speed and wind direction. The drawback to both these styles of sensors is their mounting location on the wind station, which is typically the back of the nacelle. Anytime the wind shifts direction, the turbine is essentially caught unaware of this shift until the wind has passed through the rotor, which may or may not be pointed in the right direction, and hits the wind station in the back of the nacelle. Only when this wind shift is registered can the turbine controller respond and yaw in the appropriate direction, which may be too late. This means the initial gust of the wind strikes the turbine off axis and can contribute to inefficient power production as well as excess mechanical stress. For this reason, some manufacturers are researching forward-looking wind speed measurements using LiDAR. These types of sensors can sense a change of wind speed or direction well in advance of it actually striking the turbine, and the controller can take proactive means of responding to this impending change by adjusting yaw position or blade pitch in advance, such the turbine meets the wind head-on and efficiency remains high and mechanical stress remains low. Lastly, although not sensors, the wind station often includes obstruction lighting, since it's ordinarily the highest point of the nacelle. The obstruction lights serve to warn pilots of the wind turbine's presence in low light conditions. Rather than lighting up every turbine in a farm, depending the size of the farm and the number and arrangement of turbines in a wind farm, certain patterns of light placement can identify those turbines at the perimeter of the wind farm, such that the pilot can view the wind farm as a mass rather than individual elements. In an ideal scenario, the obstruction lights are synchronized such that they pulse on and off simultaneously, outlining the entire wind farm perimeter rather than individually strobing out like a light show at a KISS concert. One more comment on obstruction lighting before I continue. Since a lot of the complaints about wind turbines tends to focus on their visual appearance, one method certain wind farms have adopted to minimize conflicts with neighbors is something known as an aircraft detection lighting system, or ADLS. Rather than pulsing the obstruction lights on and off all night, whether there's an airplane there or not, a wind farm using an ADLS only turns the light on when there's an airplane there and turns them off if the sky is empty. Makes sense. Turn the lights on if you need them, turn them off if you don't. If I could only teach my kid this lesson. Let's now return to the rotor and examine the primary components in slightly more detail. The rotor is composed of 3 blades affixed to a central hub, and the hub is connected to the main shaft. The rotor's goal is to capture incoming wind power and convert it into rotating mechanical power of the main shaft. By pitching or changing the angle of the tack of the blades, the rotor aerodynamically regulates the speed of the main shaft, thus influencing electrical power output. As we learned in the wind and water power lecture, a wind turbine power curve looks something like this. At the cut-in speed, when the turbine is first capable of exporting usable power, to the rated speed, that speed which the turbine reaches its rated output, the usable power output increases substantially given the cubic velocity term. During this period, from the cut-in to the rated speed, the turbine sets the pitch or angle of attack of the blades such that they intercept the maximum amount of incoming power. This being said, there's a practical limit to the capacity and lifespan of the mechanical and electrical components comprising the turbine, and beyond the rated speed, the turbine starts taking active measures to protect itself and ensure its longevity. This manifests itself as the turbine flat-laying output at the nameplate rating at speeds above the rated and below the cutout speed. One of the principal means of limiting mechanical power input is by pitching the blades such that they progressively shed more and more input wind. At speeds above the cutout speed, the turbine effectively ceases production by aerodynamically braking the rotor with an extreme blade pitch angle, and if this isn't enough, it can take additional steps to protect itself, such as yawing or turning out of the wind. Yawing out of the wind is sometimes known as furling. Additional mechanical and electrical means, which we'll examine in a moment, can also decelerate a moving rotor and, if necessary, hold it in place. The blades themselves are hollow fiberglass constructions that possess some identifiable features, notably the tip, the slender point furthest from the hub, and the root, that larger section attached to the hub, when viewed in length, and the leading and trailing edge when viewed in cross-section. As the name implies, the leading edge is that edge which first encounters moving air, and the trailing edge is that edge where air traveling on opposite sides of the blade region reconnects. When held at 90-degree pitch angle parallel to oncoming wind, the blade cuts cleanly through and transfers no mechanical power to the hub. When progressively pitched back towards 0 degrees, the aerodynamics of the blade generates lift and transfers an increasing amount of mechanical power to the hub. A blade is not a simple construct as you might think, and sophisticated aerodynamic and mechanical engineering goes into its twist, profile, construction, and rigidity. Because the tips of the blades are often highest point in an environment, often subject to inclement weather conditions, inside the blade there exist low-resistance wires which serve as a means of channeling errant lightning strikes to ground. Certain blade manufacturers use accessory aerodynamic devices called vortex generators on their surface that improve the efficiency and performance by reducing flow separation, which yields increased torque transfer. Blades are meant to be mounted as a matched set of 3, and any imbalance between them is offset with a shot box mounted inside the blade at strategic locations that ensures all 3 blades weigh the same. You might ask, what happens when a shot box errantly opens during operation? Well, the shot spills out, the hub becomes imbalanced, and you get to get on your back on a skateboard and slide down the inside of the blade and test how claustrophobic you really are as you clean up the mess and restore balance. Again, ask me how I know. All right, into the hub we go. The hub serves as the mounting surface of the blades and main shaft. It additionally houses the blade pitching mechanisms, of which there are 2 types, electrical and hydraulic. The blades are attached to the hub using a slewing bearing, similar to that encountered between the nacelle and tower, which allows the blade and hub to move relative to one another. An electrical pitch system uses an internally toothed slewing bearing, similar to the yaw ring, and a motor-driven gearbox and pinion gear. When the motor turns in one direction, the blade is pitched forward, and when the motor turns in the opposite direction, the blade is pitched back. Similar to the yaw controller, the pitch controller uses an incremental rotary encoder to determine pitch angle, as well as accessory electromechanical backup components like limit switches to indicate the limits of travel. Hydraulic pitch systems, in contrast, use a single double-acting hydraulic cylinder, or if the blades are sufficiently massive, a pair of double-acting hydraulic cylinders working in opposition to change the pitch angle of the blade. Pivoting trunnion or clevis mounts on the cylinders allow the linear extension and retraction of the rod to change the rotational angle of the blade, such that when extended, the blade is pitched forward, and conversely, when retracted, the blade is pitched back. A common method used to determine pitch angle for hydraulic pitch systems is incorporating a linear position sensor, known as an LVDT, or linear variable differential transformer or transducer inside the cylinder rod. Feedback, how much a particular cylinder rod is extended or retracted, can be used to measure the rotational position of the pitch slewing bearing, thus the blade angle. As with electrically pitched systems, accessory components inside the hub indicate the limits of travel and act as electromechanical backups to the positional data fed to the pitch controller by the linear position sensors on the cylinders.